this presentation. In this lab, I looked at the slinky drop, looking at the bottom of the slinky's position versus time. I used the physics principles of the second law of motion, drag force, and spring force. I showed the position of the bottom of the slinky versus time experimentally, and I compared this data to a computer model. As a preview of my results, I found a close match between the model and the experiment. The first physics principle I used was the second law of motion. This states that force equals mass times acceleration. A net force from gravity would mean acceleration or changing velocity. I used this to explain how a net force would affect the velocity of an object, in this case the bottom of the slinky. This would result in the object speeding up if it does have a net force, and it would result in no change in velocity if there is none. There would be also a quadratic increase of position with time with net force. Physics principle of drag force to further explain the motion. Drag force is a force opposing motion experienced by objects moving through a fluid, and in this case the slinky moved through the air, which resulted in drag force. The force of drag is in the direction opposite of velocity, and its magnitude squares with speed. The equation I used for this was the force of drag is equal to b times s squared, where b is proportionality constant, and s is the speed of the object. This also assumes turbulent drag, and the object would increase eventually, or the drag would eventually increase to equal weight force, at which point the net force would become zero, and the object, in this case the slinky, would have a constant velocity. Physics principle is the spring force. This is a force due to the stretching/compression of a spring, and it's in a direction opposite of the stretch or compression. Its magnitude is proportional to the length of the displacement seen in the equation. Force of spring equals negative spring constant times displacement minus L naught. For a stationary suspended spring, the force of the spring is equal to the weight force. This is used to show how the bottom of the spring would remain stationary as long as the part of the spring right above it stays in place. As the background of my experiment, there was a held out slinky that was dropped from a height of around 2 meters, and the conditions of the atmosphere were around standard temperature and pressure. It was released from rest, and the position of the bottom of the slinky was identified with tracker software at 1/30th second increments from the moment of the drop until the slinky nearly hits the ground. I assumed that the drag coefficient B equaled 40, which I derived from trial and error. The system was the slinky and the surroundings were the earth and atmosphere. I used Python to model the position of the slinky, and I had 9.8 meters per second squared as the gravitational acceleration and 1 kilogram as the mass of the slinky. This produced a set of values for expected position at 1/30 second intervals over 7.7 seconds. The initial position was negative 2.082 meters, which was taken from tracker data at t equals 0 seconds. I used two time intervals for the calculations. The first assumed that the weight force and the tension force of the slinky equaled each other and canceled each other out, leading to no net force and the bottom of the slinky staying in place. The second part removed the spring force component, but included the force of drag as part of the net force to show how the slinky would move once released.